Welcome to video 10 on the TTb course. This video is from part 2 of the course. In part 2, video 3 to video 10, we consider various techniques that form the foundation of reliable TT systems. In this video, the last part of the foundation section, we consider the use of third-party code libraries. The material in this video is based on Chapter 10 from the ERES2 book. As usual, I'd suggest that if you haven't read Chapter 10 yet, you stop the video now, read the chapter, and then come back and watch the video again. As in previous slides, we're going to use some defined terms here. The definitions for these defined terms are given in the ERES2 book in Appendix 1. Our focus here is on processor software. Processor software means all of the software on a given processor, including the TT layer, the task modules, the processor header, the port header, the support functions, and the HSI library. Particular focus will be on the HSI library. The HSI library means a suite of library code often developed initially by the manufacturer of the processor that facilitates use of the peripherals on the given processor and may also support low-level startup processes for the given processor. So if this is all of the processor software, the HSI library is a key component often supplied by the processor manufacturer that's used by many of the other parts of the software on the system. In many designs that I've reviewed, software development teams have gone to some effort to create appropriate code for their system, but have given little or no thought to the library code that is employed in their design. This is almost always a cause for concern. Many systems include the following library code: the HSI library, including peripheral libraries and startup code that I've just talked about, the processor test code used to support low-level power-on self-tests and built-in self-tests, including tests for stuck-at bits in memory and related problems. We'll look at the processor test code in later parts of this course. Final part of the library code that's used in some designs is the C language standard libraries. Appropriate steps must be taken in order to ensure that none of the library code can have an impact on the safety of the resulting product. For example, any and all code that is included in a SIL3 or ASIL-D design needs to be compliant with the requirements of the related standard. That's any code that's in the system. There's no point in creating perfect code yourself, going to a lot of effort to test and verify code that your team has produced, if you combine that code with library code produced by a third party that is not of an appropriate standard. There's very little way you can be sure that your system will operate correctly if you use inappropriate library code. We'll explore some of these issues in this video. Let's start by talking about some of the requirements for some related international safety standards, beginning with IEC 61508. So IEC 61508 is a base standard. It's concerned with functional safety achieved by safety-related systems that are primarily implemented in electrical and/or electronic and/or programmable electronic technologies. The standard is generic in that it applies to these systems irrespective of their application. So these are some examples of safety-related systems that fall into the scope of IEC 61508. Emergency shutdown system in a hazardous chemical plant, crane-safe load indicator, railway signalling systems, etc. All of these come under the IEC 61508 categories. IEC 61508 Part 3 has clear requirements for the situation in which pre-existing software elements are used to implement all or part of a safety function. See IEC 61508 Part 3 Clause 7.4.2.12. There are options for use of pre-existing software elements are described by means of 3 routes to compliance for a software element. These are paraphrased as follows. Route 1S is compliant development. The software element, is developed in compliance with IEC 61508. Route 2S is proven in use. This means that there's evidence available that can demonstrate that the element is proven in use. This is defined in clause 7.4.10 in IEC 61508 Part 2. Route 3S is assessment of non-compliant development, in which case the element has been shown to be compliant with clause 7.4.2.13 in IEC 61508 Part 3. So to summarize, there are 3 basic ways of working with pre-existing software elements in this standard. We either develop the code in compliance with 61508, we take the code and we provide evidence that the code works through experience of use of the software in previous systems, or we take the code that's been developed not necessarily in compliance with 61508, and we do some further work to ensure compliance with this standard. The same basic approach applies in various other standards. We'll look briefly at ISO 26262 in a few minutes. In the case that the code was developed in compliance with IEC 61508 Route 1S, we've met the requirements. In some cases, for example through use of qualified third-party library code, this may be the case. Where the code does not meet Route 1S requirements, Route 2S, proven in use, sometimes seems to be an easy option. This is sometimes the case, for example, when the development team have used the same libraries in previous products. However, in my experience, the evidence required to support a Route 2S case is very rarely available. IEC 61508 Part 2, Clause 7.4.10 lays out the first requirements for proven in use. The software library can only be regarded as meeting proven in use requirements if it has a full specification, if there's documentary evidence available through the use of the software library in previous products in exactly the same configuration for a long period, that makes it clear that the required SIL level will be achieved by the library, and if further suitability analysis and testing is carried out on the element. These requirements are not easy to meet. The software library is often not accompanied by a detailed specification. It may not be accompanied by any specification at all. Detailed records about use in the field are very rarely maintained, in my experience. For example, most hardware-software libraries that are provided with microcontrollers come with no documentation. They simply come as a set of source code. So at minimum, you'd have to produce a specification for these. Even if you have this, it's very rarely the case in my experience that there's full documentary evidence available that documents any failures or problems that may have resulted from a particular part of a software library when it's been used with previous products. If Route 2S is not an option, if claiming that the software is proven in use is not an option, then we need to consider Route 3S. This requires the following, and again this is paraphrased from the relevant parts of IEC 61508. We need to document the software safety requirements. We need to justify the use of the elements by considering the issues raised in IEC 61508. We need to draw up a design of the elements. We need to consider the integration of the element with the hardware. We need to provide evidence that the element has been subject to an appropriate verification and validation process. Where the element provides functions that are not required in the safety-related system, then evidence must be provided that such functions will not prevent the element from meeting its safety requirements. In other words, if there are parts of the library that are not directly safety-related, we need to provide evidence that these parts of the library will not interfere with the safety capabilities of the library. Where there shall be evidence that all failure mechanisms of the element have been identified and that appropriate mitigation measures have been implemented. So what can possibly go wrong with your software library? How are you going to work out that something's going wrong, and what are you going to do about it? And you also need to consider the configuration options used by the software element. These must be clearly identified, so you need to work out what configuration settings might be used with a particular software library, and consider all of the options and make sure there are no dangerous configuration options, for example. What this means in practice is that existing library code may be used as a proof of concept, but it needs to then essentially be recreated in a manner that's compatible with IEC 61508 requirements. This is not a trivial process, and time needs to be allowed for it in the project schedule. In my experience, people often simply don't allow enough time to do the required work on the software libraries in the development process. What about ISO 26262? The process of qualifying third-party library code is discussed in ISO 26262 Part 8 in Clause 12. In summary, we require the following: a specification for the software component, evidence that the software component complies with its specification, evidence that the software component is suitable for its intended use, and evidence that the software development process for the component was based on an appropriate national or international standard. Overall, this is, not surprisingly, very similar to the Route 3S process described in IEC 61508. The similar concerns and process need to be followed. Final category that I'd like to consider here is called SOUP. This acronym arises from IEC 62304. IEC 62304 is concerned with the development of software for use in medical devices. The standard notes that software is often an integral part of medical device technology. The standard notes that the effectiveness of a medical device that contains software requires knowledge of what the software is intended to do and demonstration that the software will fulfill such intentions without causing unacceptable risks. IEC 62304 requires that the manufacturer of the device assigns a safety class, Class A, Class B, or Class C, to each software system. Class A means no injury or damage to health is possible. Class B means non-serious injury is possible. And Class C means that death or serious injury is possible. IEC 62304 defines a software item that has already been developed, is generally available, and that was not developed for the purpose of being incorporated into a medical device as SOUP. By this it means software of unknown provenance. The use of SOUP is considered extensively throughout this standard, and the approach is slightly different to that described for IEC 61508 and ISO 26262. One reason for this is that some medical systems rely in part on the use of COTS operating systems, e.g. Linux or Windows, and it would not be practical to rework this software in the manner that is usually assumed in standards such as IEC 61508 or ISO 26262. It's probably fair to summarise the approach in IEC 62304 as one of segregation and containment. So the user of SOUP in compliance with IEC 62304 must specify the functional and performance requirements of SOUP items, specify the hardware and software requirements of the SOUP items, identify the level of segregation necessary for controlling risk, including the potential need to run different software elements on different processors, and verify the software architecture to ensure, for example, the correct operation of any SOUP items. One way we can sometimes achieve this in a TT design is to use a form of TT wrapper, which is a form of warrantor design, to wrap up and contain the failure of any SOUP items in the system. We'll say a little bit more about this in a later video on the course. So sometimes we can use TT wrappers in combination with SOUP items in our design. That brings us to the end of this video. Before you watch the next video, please read Chapter 11, Appendix 7 and Appendix 8 in the ERES2 book. Thank you for watching.